Let's talk about the air in our buildings. Not just whether it's hot or cold, but the incredible amount of money it costs to keep it both comfortable and safe. Hidden away inside these massive ventilation systems, there's a piece of tech that's completely changing the game. It's making our buildings smarter, cheaper to run, and way more efficient. We're going to dive into how a simple pipe, completely reimagined, is having this huge impact.
So why does this even matter? Well, the stakes are pretty huge. In any large building, the HVAC system, heating, ventilation, and air conditioning, is an absolute energy monster. We're talking anywhere from 40 to 60% of the building's total energy use. And a giant slice of that comes from doing just one thing: heating or cooling fresh air from the outside.
All right, so here's how we're going to break down this story. First, we'll look at the high price of fresh air. Then we'll get into the old technology and its pretty serious flaws. After that, we'll unveil the three-dimensional fix, see how it holds up under pressure in the lab, and finally look at the real-world impact for creating much smarter and greener buildings.
Okay, let's get to the heart of the problem. This isn't just about being comfy. In some places, the air you breathe is literally a matter of life and death, and making sure it's safe comes with a really steep price tag.
Just imagine a hospital operating room for a second. You can't just recirculate the air in there. That's a recipe for disaster, spreading germs everywhere. Nope. Regulations demand a constant, non-stop flow of 100% fresh air from outside. But, of course, you have to heat that air up in the winter and cool it way down in the summer. And doing that 24/7 for these massive volumes of air, well, that's exactly why HVAC systems are one of the biggest costs for any hospital.
Now, for years, engineers have used this really clever trick called heat recovery to try and cut down on these costs. But the traditional tech they were using, well, it had some pretty big limitations.
The device at the center of all this is called a heat pipe. The easiest way to think of it is like a heat superhighway. It's basically a sealed tube with a special liquid inside. On the hot side, the liquid evaporates into a gas, zips over to the cold side, turns back into a liquid, and releases all that heat it was carrying. Then it flows back to the start to do it all over again. And here's the really cool part. This whole cycle has zero moving parts and uses zero extra energy. It's totally passive.
But the old-school design was flawed. Its effectiveness was pretty low, which meant a lot of energy was still just being wasted. And because of the way it was built, there was a real risk that the stale air going out could mix with the fresh air coming in, which for hospital is an absolute non-starter. It also had to be installed at a specific angle to work right, which made things tricky. And maybe worst of all, it needed a big temperature difference, like 8 to 10 degrees Celsius, just to kick into gear.
And this is where things get really interesting. Instead of just trying to improve the old design, researchers completely reimagined the whole thing by adding another dimension.
The source paper calls this a three-dimensional thermal circuit, and that phrase is everything. See, this isn't just a simple pipe anymore, it's a whole interconnected network. The tubes are woven into this complex, snake-like pattern with rows stacked on top of each other. This lets heat move not just from the hot side to the cold side, but also between the rows themselves. It creates this incredibly efficient system.
So what does this new design actually get you? Well, the benefits are huge. It can move way more heat, but it takes up less space. It also reduces air resistance, meaning the fans don't have to work as hard. And get this, it starts working with a temperature difference of just 1 degree Celsius. Plus, because it's a totally sealed system, that risk of cross-contamination is completely gone. It basically fixes every single problem with the old 2D model.
Okay, so on paper, this thing sounds amazing. But, we got to see the proof, right? Does it actually work? To find out, the researchers built this special climate chamber to really put the 3D heat pipe to the test under perfectly controlled conditions.
The setup itself was pretty straightforward, but really smart. They made one hot chamber, that's the warm, stale air getting kicked out of a building, and one cold chamber for the fresh air coming in. The 3D heat pipe unit sat right in the middle, separating the two. Then, they just pushed air through both sides and measured the temperatures at all 4 key points: hot air in, hot air out, cold air in, and cold air out. That data tells you exactly how well it's working.
So first test, what happens when you really crank up the airflow? Well, as the volume goes up, the effectiveness goes down a bit. At a really low volume, it's an incredible 83% effective. Even when they're blasting 10,000 cubic meters an hour through it, it's still at a super respectable 63%. And this totally makes sense, right? The faster the air zips by, the less time it has to transfer its heat. Next up, they tested how the temperature of the hot exhaust air changed things. And here, the results are wow.
They're dramatic. When the hot air going in was 30 degrees Celsius, the system was 54% effective. But when they cranked that up to 40 degrees, the effectiveness shot up to 77%. The bigger the temperature gap between the two airstreams, the stronger the driving force for heat transfer. It just makes the whole system work harder and way more efficiently.
But what about the actual speed of the air moving through the system? This is where that 3D design really shines. It's all about finding that perfect sweet spot, this trade-off between how fast the air moves and how much surface area it gets to touch.
And check out how this plays out. The researchers kept the airspeed constant, a pretty quick 2.5 meters per second. With just 2 rows of pipes, the effectiveness was kind of mediocre, only 34%. But by bumping that up to 8 rows, the effectiveness more than doubled to 70%. The takeaway here is massive. Those extra rows in the 3D design create so much more surface area for the air to touch that it completely makes up for the short contact time you get with high-speed air. It's brilliant.
Lab results are great and all, but the real question is, how does this thing hold up in the messy, unpredictable real world? So the team did the ultimate test. They installed the unit in an actual hospital and watched it for a full year.
And the real-world results absolutely confirmed what they saw in the lab. In the winter, with the indoor exhaust hovering around 20 degrees Celsius, the system hit 66% effectiveness as long as the outside air was at least 11 degrees colder. In the summer, with a room temperature of about 22 degrees, it hit 64.5% effectiveness with just a 5-degree difference. This gives building managers a crystal-clear playbook on how to get the most energy savings all year long.
So let's just boil all of this down. What are the big takeaways? This 3D heat pipe is just flat out more efficient than the old designs. Its smart, compact shape saves a ton of valuable space. Its completely sealed design makes it perfect for places like hospitals where you can't have any contamination. And the bottom line is, by just passively recovering heat that would otherwise be wasted, it directly slashes a building's energy bill and its carbon footprint.
You know, we've spent all this time talking about just one little component, totally hidden away inside a ventilation system. But it really shows how just rethinking the shape, the geometry of a simple old technology can have a massive impact on energy efficiency. And it kind of leaves you with a big question, doesn't it? How many other invisible systems that we depend on every single day are just waiting for a similar kind of brilliant fix to help us build a greener future?